Alright, hi everyone, welcome to my YouTube channel, City of Electrons. And in this video, we are going to continue from the last one. That's where we stopped in the last video. But before we do that, what we are going to do in this video actually is clarification on some points, some things we need to understand to work with Maxwell's equation. Already we've seen that Maxwell's equations are four equations that tells us how electric and magnetic field behave and interact. Okay, now it can be expressed both in differential and integral form. This I want to explain from in this video. What do we mean by differential and then integral form? Maxwell's equation in integral and differential form. Note that Maxwell's equation is about electric and magnetic field. We've known that already. Now, let the electric field intensity, let's use that as E. Okay, electric field intensity, let's use that as E. Why do I have this bar on top of it? Because the electric field moves where in three dimensions. So we have it in this axis, we have it going in this axis, we have it going inside this x, y, z in three dimensions. So you need three coordinates. Okay, so the electric field exists in three dimensions. So of course it's a vector, okay, because it has magnitude and direction. So we put that thing on top of it, indicating as a vector. So you see the reason why we study vectors in field theory 1. We have to do vectors in field theory 1 because electric fields are vectors. Okay, now okay, clear with that. So this will represent our electric field E. Of course it can be any later, but just to work with what we have in many textbooks, like the conventional representation, E for the electric field intensity. That is, if we have the lines closer, that's more intensity. But if we have the lines further away from each other, that's less intensity. Okay, so this is electric field intensity. Now, of course, it's generated from a source, okay, positive, and goes into another negative. Clear now? Although these lines are not perfectly drawn, but we get the point. Please watch the previous videos, okay? Because we've done this in the previous video. We've done this representation in this diagram from drawing. Now, I hope we are clear with what we mean by electric field intensity, E. What about for magnetic field intensity? Okay, for magnetic field intensity, that's H. Clear? So this for electric field intensity. That means how intense is the field, is the electric field. How intense. That's E. Then H is how intense is the magnetic field. How intense the magnetic field is. That's H. Are we together? Then there is something. If we have a sphere here, okay, a sphere. I hope this is well drawn. Okay, now this electric field, if it passes through the surface, okay, electric field flowing through a surface, note that it's not only electric field though. Any substance that flows through a surface, that flow is known as flux. Are we together? That flow is known as what? Flux. That means flux is the amount of substance flowing through a surface. Are we together? So what we say for electric field, if the electric field flows through the surface, remember, bear in mind that, okay, let me just say that first. If the electric field flows through a surface, we say that is what? Electric flux. Because we just said that flux is the amount of substance flowing through a surface. In this case, what is the substance? Electric field lines. So if electric field lines flows through a surface, it's known as what? Electric flux. How do we represent that? There's already a symbol for that, so we'll work with that. Okay, there's already a symbol for that, which is what? D, and it's also a vector D. Okay, let me take this away from here. So D is what? The electric flux density, meaning the amount of electric field lines flowing through the surface. Note that this flux density, amount of electric field line flowing through the surface, it is equal to what? It is equal to the electric field now. Okay, it depends on the electric field, because if the electric field is intense, it will affect the flux. But it's not just only E. The flux equals the electric field multiplied by the substance. What do we have here? What is between an electric field and a surface? Air. From this source, that means the electric charge, which creates electric field. This electric field that flows from the electric charge through the surface, there is something in between, which is what? Air. There is air in between. So how does air respond to the electric field? Are you listening? How does air respond to the electric field? The way a substance, in this our case air, the way a substance responds to electric field is known as what? Permeability. That's the name for it. Okay, that's the name for it, and this is how you write it. Epsilon naught, permeability. Permeability. So the flux depend on how this thing how the substance, how air respond to what? Electric field. So flux will be what? How air respond to electric field multiplied by electric field. So that will give you the value of flux. That will give you the value of what? Electric flux density. Okay, so we've said that this one is for what? Electric field. Electric. Okay, let me take this one out first. So since we've done that, we can now say that is dividing both sides by permeability, electric flux density equals epsilon. If we divide both sides by epsilon naught, we have what? E. This one goes under. Okay, this guy goes under. I just change the side, so you now have D all over what? Epsilon naught, which is this D all over epsilon naught. So that's the electric field intensity. Are we clear? So just bear this thing in mind. We will need them in the next video. We will need these things in the next video. Please understand this, please. Okay, so we've done that for electric field intensity. Now, what about for magnetic field intensity? Similarly, for magnetic field intensity, it is just like this. However, let me put it this way. This for the field intensity, for magnetic field intensity. So if, let me put a magnet here. Okay, north and south pole. Let me use a magnet this time. But what's happening now? So for a magnet having north and south pole, of course, okay, so for a magnet, this flux, this magnetic field, remember, this is a field, but it's created by a magnet, so it's called magnetic field. So this magnetic field, how intense is this magnetic field? That will be giving us what? H. Are we together? That's H. Now, the amount of magnetic field lines flowing through a surface is known as what? Magnetic flux density. Magnetic flux density. And what do we use to replace it? B. Are we seeing it now? Now, the amount of magnetic field flowing through the surface depends on the intensity and what? How what we have here? Air. Or whatever substance we have there, how that substance respond to the magnetic field. We use what? This mu 0. and it's known as what? Permeability. I like your name. Permeability. So the magnetic flux density equals permeability multiplied by magnetic field intensity. Okay. Now, pardon me, I didn't write I didn't type it out, but just listen and be blessed. Listen and get the point. Okay. So this is the two things you need to have in mind. Let me just make magnetic field intensity subject formula, and that will be this. Okay, you just divide both sides by this, and this guy will be equal to B over permeability. Magnetic flux density over permeability. Okay. Now, when we say Maxwell's equation in differential form, this is what we simply mean. We have this. I'm using electric field for it. Okay. It applies to both magnetic and electric field. But let me work with electric field for it. Now, these are different charges, electric charges. Are we together? These are different electric charge, right? Positive or negative. Now, if we consider all together, isn't this summation from these points to these points? If we take, but the thing is this, the intensity of the field created by this electric charge will be different from the intensity, or may be different from the field intensity created by this charge, and so on. So what do we do? To consider all of them, all the charges, to consider all of them, we take the integral. Are we seeing it? That is integral form. Is in a way like summation of charges, or summation of summation. But if we say differential, we are just taking what? 1 point, because we separate now. Differential, separate, break down, we take 1 point. That is why sometimes differential form is also called point form. Okay. So I think I won't say more than that. That's just the basic difference between these two. Just a single approach, just a point, and then sum of points, like that. Okay. So so that's that. Then for the 4 equations, you can look at them as this. 4 equations, right? But you can look at them as this, split into 2. Okay. Electric field, or let me put it this way, split into 2. Generation, and then behavior. Okay. So how is electric field generated? How is magnetic field generated? How does electric field behave? How does magnetic field behave? These are your 4 equations. 1, 2, 3, 4. That's it. Are you seeing it? So with this approach, it simplifies the 4 equations for you. It makes it easy. It makes the 4 equations easy for you to look at. Okay, at least you now see the relevance that the 4 equations are divided into 2. You can look at, and these 4 equations be divided into 2. 2 of them tells us generation, which is generation of electric field, generation of magnetic field. Then the other 2 tells us, one tells us behavior of electric field, the other tells us behavior of magnetic field. However, I think there is one of the equation, this one. There's one of the equation that tells us both generation and behavior. But basically, this is how the equation of Maxwell looks like. Okay. So from all we've been talking about, like these guys, okay, you've seen the part where we talked about this guy, these guys, and the part where we talked about this guy, okay, and what we talked about point and integral, which is differential and integral. So this is Maxwell's equation in differential form, which is the same thing as point form. So if you watch that part where I talked about differential and integral, you understand what I mean by differential meaning as point form. Okay, so now the four laws of Maxwell are Gauss's law of electric field, Gauss's law of magnetic field, Faraday's law of induction, Ampere's Maxwell's law. Remember I said these four laws are about two things: electric field and magnetic field. Look at this first one, it's for electric field. This third one is also for electric field. Are you seeing it? Second one, magnetic field. Fourth one, magnetic field. So you can see I won't highlight them. Electric, electric, magnetic, magnetic. U and U, generation. Okay, U and U, behavior. Although this guy also has generation inside of it. Okay, that's why I explained here. Okay, are we seeing it now? Now let's take the first one. So for Gauss's law of electric field, it states that electric fields diverge from electric charge and the electric flux density equals charge density. Okay, hold on. Electric fields diverge from electric charges and the divergence. Yeah, this makes sense. Divergence of the electric flux density equals charge density. Okay, now it's this what we mean. This what we mean. That if we have this, before using this other guy, you have this as a surface. I think I've drawn something like this before. Okay, and you have of course positive, negative. It flows like this, isn't it? Flows like this. Okay, now electric field diverge from electric charges, so it comes out from the positive end, it's going out, negative end is going in. So if your divergence is positive, it means it's going like this. Divergence is positive, it's going like this, out. If it's negative, it's going out, positive. But if it's negative, it's coming in. Guys, what do you think if it's zero? If the divergence is positive, it's going out. If divergence is negative, it's coming in. If divergence is zero, what's happening? No in or out, just like no, it's not coming from anywhere. Okay, so this one indicates there's a source, like it's coming from somewhere and it's going into somewhere. Positive coming from somewhere, negative going into somewhere. Okay, so that's for that. Oh, this is wrong. Okay, so that's for that. Let me just take this out. So that's for that. Clear? Now, what if? Yeah, that's for that. Then the next thing they said is, and the divergence of the electric flux density equals charge density. How do we represent electric flux density? We've said that before. Electric flux density is represented as D. Is that not so? Electric flux density is represented as what? D. Now they are saying that for the first law, that the divergence of the electric flux density. How do you write divergence? It's written as this. Nabla dot. This is how to write divergence. Like this. This whole right up here means divergence of electric flux density. Are you seeing it? Divergence of electric flux density. Divergence. That's Nabla dot electric flux density. So all these sentences, we just squeeze them using symbols. Perfect. Save your ink. Okay. So it's equal to what? Equal to charge density. How do we represent charge density? Well, like in many textbooks, this is how you see it. Rho. The divergence of electric flux density equals what? Charge density. Recall that we said electric flux density D equals to what? Look at it here. Epsilon naught multiplied by what? Field intensity. Yeah, this is it. I told you we are going to make use of it. D equals what? Epsilon naught multiplied by field intensity. So if you substitute that there, here, you get what? You get what? Divergence of what? Epsilon naught, and this equals rho. Are you seeing it? Then if you make the subject formula, this guy goes down. Okay, like divide both sides by it. Okay, what will you get in that thing? What will you get? You have this. Okay, you have this. This, my friend, is the first law. Okay, this is how you write it in point form. That's differential form for Gauss's law of electric field. This is it. Okay, this is it. Next, we'll go into the second law. And the next thing is Gauss's law for magnetic field. So we've seen this one, electric field. Now for magnetic field, remember we drew something like this, saying that the magnet, no, I already have that drawing. Come this way, I already have that drawing here. Yes. So you see that for magnetic field, okay, there is no, this, we just have one magnet, okay, not two magnets. But this one magnet always have a north and a south. So if you say, okay, fine, let's divide this magnet in two, so that we'll have just one part. If you divide the magnet in two, even this magnet will give you, now we have two magnets, right? Inside that magnet, you still have your north and south. North and south. Okay? So this just indicates this. Look at the definition here. It just indicates the non-existence of magnetic monopoles. Now, magnetic field lines, they have no beginning or end. No beginning or end. So what will you say? Look at this guy now. Where is the beginning? It's just like a rubber band. Okay, where is the beginning of the rubber band? Or a ring? Where is the beginning of the ring? Where is the end of the ring? None. So it has no source nor end, like beginning and end. So, and we said that if the divergence is going out, is what? Positive. If it's coming in, is what? Negative. And if it's not going out or coming in, it is what? Not going out or coming in, is what? Zero. That is where is this guy? No. That is, let me clear all this space, Let me clear this space. Clear. That is the divergence, which is this nabla dot. The divergence of the magnetic flux density equals what? Zero. Are we seeing it now? The divergence of the magnetic field, the divergence of the flux density of the magnetic field equals what? Zero. Now if you say, okay, let us check for the intensity. Remember, we already said that magnetic flux density equals what? Permeability multiplied by magnetic field intensity. That means magnetic field intensity equals what? Isn't it? So if you substitute, what am I doing? No need for this other part. If you substitute this into this part here, you have it as this. Okay, you have it as this, which is the same thing as saying, hope we are following. And then of course that will still give you what? Zero. Okay, but in most textbooks you will just see it like this. You will just see only this part. You will just see this part. Okay, but if you see it as that H is still correct, so I think I should just leave it like at this. Okay, should just leave it at this. So you can go with this formula for Gauss's law of magnetic field, or you go with this. They are correct. Okay, the next thing is Faraday's law of induction. Okay, this is the next law, Faraday's law of induction. Now the law says that a time varying magnetic field induces a circulating electric field. This is all you need to write out the formula, to write out the equation, which is mathematical expression. Okay, but let's just read the rest part. The induced electric field circulates in a direction that tries to oppose the change in the magnetic field. Now what does this mean? Let's write out the equation for this. What does that mean? A time varying magnetic field, that means magnetic field, right? And we say it varies with time, which means it changes with time. Are we saying it? But take note, this magnetic field, it is what? Multi-dimensional. That means it changes in the y-axis, changes in x-axis, and it changes in what? Z-axis with respect to time. Okay, that means there will be a differentiation, a partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. That means what we have here is what? This partial or partial. That's what we have there. Okay, now according to this law here, notice that all we are doing right now is just to give a mathematical expression of what the law states. So they said a time varying magnetic field, which is what we have here now. Okay, what happens? It induces a circulating electric field. That means this time varying magnetic field causes us to have what? An electric field, which is what? Circulating. And how do we write that? Circulating means coil. Circulating now, that means circulating coil. So, and in order to write coil, you do this. This whole thing here means coil. Okay, nabla cross, it means what? Coil. So this definition here just means this. Okay, so it means a time varying magnetic field induces a circulating field. Time varying magnetic field. And I explain why we use partial derivative just now, because it's more than one dimension, x direction, y and z. So this time varying magnetic field produces or induces a circulating electric field. So this is the circulation coil, nabla cross, circulating electric field. But note that the induced electric field circulates in a direction that tries to oppose the change in the magnetic field. That means the circulating electric field is opposite the magnetic field. Okay, so we can actually write this as saying this equals negative this over this. You can do it like this way. Okay, so this is the equation. Okay, this is the equation for it. Okay, exactly. Please, if you have questions, please leave it in the comment section. Okay, so this is the equation for that. So we'll go to the next one now. Next, so Ampere's Maxwell's law. So magnetic fields are produced by conduction current and by time varying electric field. Note that for this case, it's for electric field. Okay, now in this case, that's the next case. Now Ampere's Maxwell's law is for what? Magnetic field. It's for magnetic field. Okay, so magnetic fields are produced by what? Conduction currents. So we'll have this. Note that the magnetic field produced in this case is what? Circulating magnetic field. Circulating magnetic field. So just like we said about this, when we say circulation, this is what we mean. Nabla cross, which is coil. Okay, so coil. Okay, magnetic field are produced by conduction currents. So this is current now. Current. Okay? Current. I or J. Okay? I or J, whichever one you want to use. So now that's this conduction current. But of course, since we are talking about magnetic field, we have to include, let me just complete this other part first. Produced by what? Conduction current and what? Time varying electric field. Time varying electric field. So we have electric field, which is what? Changing with time. So we now have what? This. But like we said in the previous one, this field is in 3 dimensions: X, Y, and Z. So it's more than 1 dimension. That means we have to have partial derivatives that will change in each of the dimension. Okay. So I hope this part is clear. Okay, that this magnetic field is produced by what? Conduction current and then time varying what? Electric field. But the thing is this, there are constants. Okay, so for our conduction current, note that we are talking about this guy. Is that also? We are talking about magnetic field, and how much a substance responds to magnetic field lines is known as permeability. We've said that before. Okay, so if you have watched this whole video and the previous one, you understand what we mean by permeability. So we'll have it like this. Okay, also we have it here, permeability. Okay, but in this case we are not going to have only permeability because of this, yes, but look at this. We have what? This electric field here. Okay, so therefore, and for electric field, how much a substance respond to electric field is what? Permittivity. We've also said that, so you have it here. Okay, so this gives us the complete equation, and all these are in what? Differential form. So this gives us the complete equation. So we now have all 4 equations in differential form. Okay, let's see all we've done. Yeah, yes, so these are the equations in differential form. So we've gone through them, explained, and then gave the expression. We're going to explain the expression. Same thing here, the definition and then the expression. The definition, which is the law, and then the expression. Definition and then expression. Definition and expression. Okay. So in the next video, we'll talk about the integral form. These are just the differential form, which is just a point. Integral form talks about a range, surface, giving range, okay, especially over a surface, okay, or what's inside a volume. Okay, so we'll stop here in this video. So like, share, subscribe, and I'll see you in the next video. Thanks for watching. Bye for now.